Here in section 1.3, we'll take on the concept of measure. This is where we assign numbers to various kinds of geometrical objects, a very common kind of maneuver in this class. If you don't know precisely what that means, well, actually you do. You'll find that this is actually quite familiar. So in the first semester, we give measures of two types. In the second semester, we'll add another type of measure to this, but in semester one, we do measures of two types. The first is measures of segments, often called length, and the second is measure of angles, which, as I suspect you know, is often given in degrees. So let's talk about each of these in turn, what we mean by measure of a segment, measure of an angle, and I'll also have to provide for you a pair of postulates along the way. So before we hop into this, do make a distinction here. Measures are real numbers, okay? Or if you like, just simply numbers. They're not geometrical objects. So, it's like 2 or 2.5 or pi or whatever it is. They are numbers. So we will associate certain geometrical objects like segments and angles with numbers, real numbers in particular. So length defined. This is not something that we'll worry about too much. You're very familiar with it. It's the basic idea behind a ruler. So to get the length of a segment, first of all, we have to establish a unit of length, and common choices are like centimeters, inches, miles, kilometers. Doesn't really matter what it is for us, but we'll assume that a choice of unit has been made. And then when we report the length of a segment, what we said is that it takes that number of the unit to cover that particular segment. So for instance, if we say that the measure of a segment or its length is 2.3 centimeters, what we mean is that it takes precisely 2.3 of the centimeter unit, whatever length that is, to cover our particular segment. This is something that should be very familiar to you. It's basically what you do with a ruler, for instance. If you lay a ruler against a segment and you find that it says 2.3, what that really means is that it takes 2.3 of the unit on the ruler, whatever it happens to be, commonly centimeters or inches, to stretch from one endpoint of your segment to the other, that is to completely cover it. Now, in this class, typically we won't report the units of length measure. We won't say, for instance, centimeters or inches or whatever it is. This really ought not to bother you. You instead ought to feel as if a burden has been lifted from you. In most instances, I will not require that you report the unit of length measure. We will just simply assume that one exists, whatever it happens to be. Now, we'll need to make an assumption about lengths. Actually, we'll need to make a multi-part assumption, but I'll only give you part of that assumption right now, and it is called the ruler postulate. And that part of the ruler postulate that I will give you today says simply this: every segment has a positive length, whatever that happens to be. Again, of course, we assume a particular unit here, but given the choice of a particular unit, it will follow, we assume, that every segment has some positive length, whatever that happens to be. Now, we need to make a distinction here. We need to make a distinction, as I've mentioned before, between a segment and its length. And since we make this distinction, we need to have a different way to symbolize these two. So the segment itself, as we know, is given by its endpoints, like for instance, AB with the segment symbol on top, or equivalently BA with the segment symbol on top. That designates the geometrical object. But if we wish to designate, if we wish to name the length of the object, well, one way to do it is to simply write the A and the B side by side with nothing on top. I don't much like this symbolism, but it is commonly used in geometry and we will commonly use it. So do know that if you see two capital letters side by side with nothing on top, that designates the length of the line segment AB. Or another way to do it, which I suspect is clear, is to write the AB with a line segment symbol on top and then the M in front of it, where the M is short for measure. And then that would be read as the measure of line segment AB. Okay, so we have an illustration for this. On the bottom, we have line segment AB, which you're clear about this, aren't you? The line segment is a collection of points arranged in a particular fashion, the straight fashion, I suppose. And then the segment length, designated as simply AB, nothing on top, or M, segment AB, is a number. Okay, so they're both mathematical objects, I suppose, but they're different kinds of mathematical objects, and the number is associated with the geometrical object and gives its length. Now, As for diagrams, how we indicate the length of a segment on a diagram, we just put it right in there, very often near the middle of a segment. So if you look at the diagram itself says that segment BC has length 2 and segment AB has length 5. And of course, we can write that symbolically as AB, nothing on top, equals 5, and BC, nothing on top, equals 2. Now, we can also say or have a diagram say that a pair of segments are equal in length, even if we have not said precisely what those lengths are, and we do that with hash marks. So you'll notice that our segment AB in the diagram has a hash mark on it. The segment CD also has a hash mark on it. And notice that they both have precisely one hash. And what that then means, what the diagram says to us, is that the length of AB is the same as the length of CD, which we can also write symbolically as AB is equal to CD. Of course, we can also use multiple hashes as well. So notice in the diagram that AB and AG both have a single hash. Notice that AC and AF both have a double hash, and that AD and AE both have a triple hash. So the diagram has said to us, as surely as if we had written these words out ourselves, that AB and AG have the same length, that AC and AF have the same length, and that AD and AE have the same length. Now, of course, a very good question here is this, is that has the diagram said that, for instance, AD and AC have different lengths because they have a different number of hash marks? Well, short answer, no, it hasn't said that, but do know that we will take up this question about what diagrams say to us and what they do not say in the next section. It's actually a very important topic, a source of many pitfalls in this class. But do note now that this diagram has not said that any segments are unequal in length. All it said is that segments are equal in length. All right, midpoint, this is the place to define that, I suppose, because it has to do with segment length. So let us say that we have a segment like AB in the diagram, and let us say that we locate a point C in its interior such that the two parts that result are equal in length. In this case, we dropped C into the interior of AB so that AC is equal to BC. We say in this case that C is the midpoint of segment AB. A very natural definition, of course. Now, let's turn from length, that is measure of line segments, to the measure of angles. And I'm sure you'll be quite familiar with this as well, so I'll go through it quickly. We said about length that we will typically leave our unit of segment measure, that is of length, implicit. We won't do that with the unit of angle measure, however, because we want to make sure that the number that we use to report an angle measure is not confused with the length. And we will do that in the standard way. In a course like this, we will use degrees, and we will use the degrees symbol, which is that little circle raised off the line. And by definition, a degree is 1/360th of a complete revolution of a ray about its endpoint. So what you're to imagine is that you have a ray, which, as you know, of course, is a half line, and you imagine that you anchor its endpoint and you allow the ray to rotate about that fixed endpoint. And a degree then is 1/360th of a complete revolution about that endpoint. So let us say now that we have an angle, okay? And let us imagine that we rotate one of the sides of the angle until it coincides with the other, and imagine that the vertex remains fixed. The number of degrees through which one side must rotate until it coincides with the second side is by definition the degree measure of that particular angle. And of course, it would be good here to have an illustration of that, so here it is. So we have angle BAC. So let us imagine that if we rotate side AB, the ray AB, with A fixed until it coincides with AC, and if, as we do this, we sweep through 120 degrees, then we say by definition that the measure of the angle is 120 degrees. So really, lengths, to sort of sum up what we've said so far, lengths are, of course, straight measures, right? It's about how far you have to go from one point to another point in a straight path to get from that first point to the second point. So length is really, in a way, straight line motion. Degree measure, on the other hand, that is the measure of angles, is rotational measure, right? We ask ourselves how much we must rotate one side of an angle so that it will coincide with the second side, and however many degrees is that, that is the measure of our angle. Now, an obvious question here is this. When we do this rotation of one side of an angle until it coincides with the second side, is this clockwise rotation or is this counterclockwise rotation? Of course, we could go either way. And typically we get different answers if we go clockwise instead of counterclockwise. So in the diagram, if I get 120 degrees, if I rotate AB in a counterclockwise fashion, I would get 240 degrees, of course, if I were to rotate it in the clockwise fashion. Now, the question again is which of these is correct? Well, they're both correct. So typically, except in one very special case, angles do have two measures. Those measures will always sum to 360 degrees, but still they have two distinct measures. So which one do we choose? Typically the smaller. This is what we will almost always do. And if we ever need to choose the larger, I will say explicitly, let us choose the larger. So you will do what's quite natural here, what you've always done before. You will choose the smaller of the two possible measures of an angle. Now, how do we specify angle measure? Well, we can do that with the diagram. We can tuck the angle measure into the interior of the angle and, of course, put the degree symbol on it. So notice in my diagram that we've said that the measure of angle A is 28 degrees. But we can also say that with a statement that makes use of the equal sign. We write measure, M for measure, angle symbol, and then A equals 28 degrees. And that will be read as the measure of angle A is 28 degrees. Now, we had a ruler postulate, which told us a little bit about how lengths behave. So let us now have a protractor postulate, which tells us a little bit about how angles and their measures behave. And this will be only part of the total protractor postulate that we will get, but we only need a part of it right now, so I'll give you that one part. And it says this: every angle has a measure, and that measure is greater than 0 degrees and less than 360 degrees. And I think that you will find that quite plausible. An angle, of course, is two rays that share a common endpoint, so there will be some number of degrees that it takes to rotate one side until it coincides with the other. This will have to be greater than 0 and less than 360, and this is our protractor postulate, or at least the first part of it. Now, we found that we could make a diagram say that lengths are equal. We can also have a diagram say that angles are equal as well, that is, have equal measures. And we do that with hash marks, but we do that with hash marks that are placed on arcs in the interiors of the angles. So look at my diagram. Look in particular at angles BAC and angles DAC. Okay, again, BAC and DAC. Notice that those two angles both have an arc in its interior, a shaded arc, and then we have hash marks on those arcs. Let me circle them for you. So then the diagram says that angles BAC and DAC have the same measure, whatever that happens to be. And likewise, the angles EAF and FAD, they both have arcs in their interior, shaded arcs, and they both have two hashes on those arcs. So the diagram also says that the measure of angle EAB, is same as the measure of angle FAD. And we can also write those, of course, out in equation form. So there it is, the measure of angle BAC is equal to the measure of angle DAC, and the measure of angle BAE is equal to the measure of angle DAF. So we can say it both in statement form with the equal sign, and we can also have diagrams speak to us and say that angles are equal in measure, just as they could say that lengths are equal in measure. Now, we defined midpoint, so let us also define angle bisector, and this is a place to do that because it depends upon measure. So let us say that we have an angle, and we place a ray from its vertex through its interior so that we create a pair of equal adjacent, as it were, sub-angles. Okay, so when we do that, we say that the angle, the ray that we have placed is the angle bisector. So look at our diagram. We have angle ABC. We have placed the ray BP. I'll tell you what, I'll circle it for you. We've placed the ray BP so that we've created a pair of adjacent equal angles, notably ABP and CBP. We say in this case that the ray is then the angle bisector. So be careful about what you need to bisect a segment and what you need to bisect an angle. What bisects a segment is a point placed in the segment's interior so that you then get two sub-segments equal in length. On the other hand, what it takes to bisect an angle is a ray. You place the ray in the interior of the angle from its vertex so that you end up with two equal sub-angles. Now, just a few quick definitions of terms that you're no doubt familiar with. Let us make sure that you know how to use these correctly. We say that an angle is acute when its measure is less than 90 degrees. We say that an angle is obtuse when it measures less than 180 and greater than 90. Okay, so do note this. Obtuse doesn't simply mean greater than 90. It also means less than 180. When we say right, as I'm sure you know, we mean an angle that measures 90 degrees. And we have a particular way to indicate this in a diagram that we will very often use. We Into the interior of the angle, we drop this little shaded square, as I just circled. That says, the diagram then says that the angle measures 90 degrees. And since we've defined right angle, I suppose we should also define perpendicular, because the definition of perpendicular makes use of the definition of right angle. So here it is. Two lines are perpendicular when they form a, in the sense of at least one, right angle. Now, you might well be troubled here. You might well wonder why I didn't say that perpendicular lines form four right angles here in the definition of perpendicular. Well, my response to you is this, is that indeed perpendicular lines will form four right angles, but that doesn't really belong in the definition, because again, all definitions are supposed to do is allow us to pick out objects of a particular type. And certainly it's true that if two lines form a right angle, then they are perpendicular to one another. Later on, we will indeed prove that perpendicular lines form four right angles, but that will be something that we will actually prove, and we will not put that into the definition. Two other terms and we'll be done. Two very important terms. We will use them all throughout the class. They both concern the relationship between angle pairs. In fact, the relationship between their measures. So first, complementary. Two angles are complementary when the sum of their measures is 90 degrees. And those two angles need not share a side. And I have two examples of this for you. So on the left-hand side, you have a 60-degree and a 30-degree angle. So of course, 60 plus 30 is 90. So it follows that our two angles on the left-hand side are complementary to one another. I just circled them. And then look on the right-hand side. We also have a pair of angles. I tell you what, I'll give them names. I'll call them angle 1 and angle 2. Sorry, diagram's a little bit complex now, a little messy, but there it is. I have an angle 1 and an angle 2, and they obviously sum up to 90 degrees, right? They are simply the parts of that 90-degree angle. So we will say that they are complementary. So do keep this in mind. Complementary is only about the sum of the measures. That sum must be 90 degrees. It's not anything about how those two angles are laid out. They might be adjacent, they might share a side, they might not. And then finally, let us define supplementary, which works in very much the same way as complementary, except here the sum must be 180 degrees. So two angles are supplementary when their sum is 180 degrees. And again, they need not share a side. They need not be adjacent. So on the left-hand side, we have a pair of angles, obviously not adjacent. One measures 60, the other 120. So their sum is 180. That means that by definition they are supplementary. And then on the right-hand side, we have a pair of angles, which again I'll call angles 1 and 2, which are just the parts of a 180-degree angle. So of course, then they will be supplementary as well.